Okay, so good morning, everyone. My name is Angshuman Mazumdar, and I am a student of Purdue University, along with my professor, Dr. Christos Mousas, and we'll be presenting our paper, Synthesizing Effective Virtual Reality Multi-Character Experiences. This is how the contents are going to be for today's slideshow. Basic introduction and a little bit about crowds in real life and how crowds have been translated into virtual reality. And we state then our problem, the purpose, and finally we address some of our research questions, the assumptions and participants we used. And then we move over to our methodology. We have basically three different stages. So I explained through all of those. And finally, we move on to our conclusion and future work. Our limitations are discussed through the future work, and I will try to explain it as clearly as I can. So humans, we are social beings. It's just as has been said from time and over. We like to thrive with different people around us, and we have this innate ability to communicate through verbal and as well as nonverbal communication techniques with each other. Basically, crowds or any sort of small gatherings forms our social status in the society. However, crowds are a very overlooked aspect of our lives. It forms a huge aspect, well, at least before the pandemic. It used to be a huge thing, but now we are slowly returning back to normalcy. But crowds are this wonderful thing that exists in real life, but we tend to overlook it because it's so common around us. Crowded scenarios could be anywhere: crowded rallies, markets, concerts, and they were basically inevitable. And in real life, these crowd interactions are basically based on interpersonal communication. There are three major components to it: your nonverbal communication, body language, and all of that, hand movements, head movements, your eye gaze, where we are looking at, who we are looking at, and how long we are looking at, and proxemics, the concept of spatial zones and how there's different zones where we carry out our intimate conversations, our social conversations, and then the rest of the world. This is like our defense mechanism. Based on all of these, we have our ocean model that has been generated, which is openness, conscientiousness, extroversion, agreeableness, and neuroticism. Openness is how willing we are, our ability to how willing we are to accepting new situations and people around us. Consciousness is how disciplined we are of our own actions around these people. Extroversion is how much we express being in the crowd. So, for example, if you're extroverted and we like to interact with a lot of people, our extroversion levels are high. Agreeableness is how trustable we are around the crowd as well as the crowd around us. And neuroticism is our ability to counter complex or difficult situations. Basically, in a crowd, there's always this concept of if it's especially an unknown crowd of people, there's this concept of flight or fight. That comes into our mind. So neuroticism is basically our ability to decide between those and balance between those. So if we move over to virtual reality, most of the crowds and crowded scenarios that have been developed focus on disaster management and crowd response to those disaster scenarios, basically favoring towards the neuroticism concept of ocean model. Many of them are collaborative scenarios where you are, as a player, you are expected to be a part of the crowd and follow their actions rather than create an immersive action with the crowd. And the basic idea being that in here, the situation is targeted towards the player, where the crowd plays basically a passive role. It just exists to fill up the environment in most of the cases, at least. Here are some of the examples that came up in our literature review. These are very good examples and good papers related to crowd-related scenarios. However, a common theme is that they don't influence the mindset. Rather, they expect the player or the user to be a part of the crowd rather than the crowd doing something on the player. So that's how we arrived at our problem. We attempted to explore this automatic synthesis method where the crowd drove the user affect. Affect in this case is something that has an effect on, or something that brings about a difference in the user. And we wanted to see how design decisions got influenced when introducing these affected characters in a virtual scenario with the player. So the purpose of our study was we exposed the players to a lifelike crowd, and they had certain behavioral parameters. We optimized those parameters for the negative affect, basically something that brings about a negative change in the mind of the user. And then we try to get an emotional response from the player themselves. This is how we formulated our research question. We just have one. Is it possible to automatically synthesize multi-character experiences that induce a certain amount of negative affect in participants based on a provided level of given target negative affect? There are two reasons why we did this. One, negative affect was chosen because of previous studies which illustrated to the fact that participants appreciated the negative aspect and negative emotions more in virtual studies rather than the positive ones. And this study was limited because we wanted it to be a foundational study, basically a start of something, a start of a bigger, a bigger picture. So we decided to take it in a sort of a proof of concept way, where we wanted to explore this avenue that, whether it can exist or not. Some assumptions and details about our participants. We assume that the participants in our in our experiment had some sort of crowd-based scenario exposure to them, which is fairly common in human beings. But then again, just have to be sure about that. And was composed of the undergraduate and graduate students of our university, Purdue University. The third point about the annotation sample will be important in the upcoming slides. The annotation sample comprised of 10 students with extensive VR knowledge in all sorts of field and VR emotional studies and etc. They were mainly of the graduate students level, and they had a lot of virtual reality exposure throughout all their study life, basically. So methodology is how we broke up our experiment was basically we broke it down to 3 stages: our annotation phase, optimization phase, and final targeted phase. The annotation, we developed it because we did not have any sort of prior knowledge about how behaviors were rated inside of virtual reality. So we wanted to develop this basic starter database where we could refer to through our, like when the optimization phase started, we could refer to a certain set of values. Optimization, again, is the specific way we created those crowds and we assign them behaviors. And final targeted synthesis phase is basically us taking those optimized crowds and exposing them to the players, where they reflected on them and they gave us feedback. So in our initial background searches, we found out that our core concept was basically dependent on 2 of these concepts: the macroscopic factors and microscopic factors of crowds. Macroscopic is generally where we consider the crowd as a whole entity. These all encompass like the density of the crowd, the number of the crowd, the flow dynamics, all of those concepts. And microscopic is basically the individual composition of how each of the character inside the crowd is generated or how they behave. So in our study, we focus mainly on the microscopic factors. Here's a short flow graph of how we wanted to do it. So every phase has an expected outcome. Annotation, we have an expected outcome of a data set of behaviors, which I referred to. Optimization uses that data set, and then we generate 3 levels, basically low, medium, and high negative affect using the values in the data set. And final study, we expose our participants to evaluate whether the low, medium, high are perceived as we want them to be perceived. The instruments that we used were Unity Game Engine for developing the entire experience and the Oculus Quest for delivering the experience. We also had a questionnaire, which was basically built up on the PNAS questionnaire. We took some terms and then we developed our own questions around it. And then we used the 100-point scale to get the feedback from the participants. So experimental design basically covers the common part of all the 3 phases. Each scene was a sidewalk scene from an urban environment, which I had to build ground up because a lot of the pre-existing stuff from the asset store was too big and too complex for this set. We wanted to keep it restricted, and we didn't want any sort of distractions, so that the crowd would be the main focus of the player. The characters had certain behavior. These behaviors, we brought in animations from sites such as Mixamo, where we used certain sorts of scripting and animation layers and all that sort of techniques to blend together to form one behavior. I'll talk about the behavior more in the future slides. The player, they were only able to move their head and rather than them being fully interactive. And all the scenes that were shown were determined by Latin square design for both of those phases of the experiment. To sum it all up, we have our annotation phase, which will have 34 scenes for 34 behaviors, and one behavior is assigned to one scene. So that in this part, the experienced VR developers and the VR participants could give us a good idea of how to rank our different behaviors. And then the number of scenes in the final synthesis phase would be one for each of the three conditions, and each of them would have 10 different behaviors. So this is how the sidewalk looked like. I did not want to make it too congested, did not want to put too many elements into it. So that was, again, interesting because I had to figure out, I love level design, and this was one of the things where I was like, okay, this is an important thing where we want the environment to exist, but we don't want it to be in the the focus of the player. This is how the positions were laid out. The red is where the player would start. So to the basically from where the camera was in the previous slide, this is, let's say, where the player starts, and the end is the blue point. And in between, we have these crowd locations where randomly different characters from the crowd would be spawned in for the annotation phase as well as for the final synthesis phase. And this is once the crowd has been set in without the behaviors applied to them. This is how it looked like. Basically, you have just a sort of characters that start off, and then we decide what behaviors to apply to them. So let's talk about the annotation phase a little bit. Again, each participant viewed all 34 scenes correlating to 34 behaviors, and the characters were changed randomly. We did not want them to associate one behavior with one character. We just wanted them to focus on the behavior itself. And the idle no look state was the base state. All right, so this is how all the behaviors that we had came together. We had different common behaviors that we sought out. We started off with a huge list, and then we narrowed it down to the most common ones that we see in our day-to-day life. So we have walk across, someone walking across our path, walk towards, someone walking towards us, pointing, people pointing at us, yelling, someone was yelling at us, sidestep, basically crowd entity would step outside. They were in our path, but once we came close to them, they stepped outside of our path. And idle is just them standing around. Then we took on the concept of gaze mechanics, where there's two conditions, look at and no look at, pretty self-explanatory. The crowd entity would either look at you or they would not be looking at you. And then we brought in the concept of proxemics, which stated the three states. So you have intimate space, personal space, and social space. Together with all of these three different categories, we formed a behavior. So let's say, for example, an example behavior would be a walk across, look at, intimate, where the crowd entity would walk across our path. They would be looking at us, and they will only do the animation or the behavior when they were in the when the user was in their intimate space. So that is how we formed 34 behaviors. We had to keep one behavior as the base state because either look at no look at, intimate, personal, social wouldn't matter because they would not interact with us essentially. Here are some of the models that we pulled from the community side from Mixamo. Again, the top row shows us how the three different behaviors looked with no look at, where the entity is not looking at us. And then the bottom shows where the entity is looking at us. All of these were a bunch of mixture of scripts and animation layers, blend layers, almost. Here's how the setup of an individual character in a crowd was done. Each character had three different zones from the proxemics concept, and then they had a field of view. So essentially, in real life, people wouldn't know what's going on behind their back, right? Unless they have some sort of weird glasses that show them what's behind their back. So we wanted it to feel as realistic as possible. We wanted it to behave as real as possible. And for that, we had to think of each entity as a real entity in a crowd. And this is how the questions look from the Panas questionnaire. We took four points from the Panas questionnaire. So upset, alert, nervous, and distressed. And then we also had some space where the users could fill out their comments. Basically, they had a slider and they could just slide around and give their opinion on it. So it ranged from 1, where 1 was not at all, to 100, which was extremely annoying or extremely upset. So here are the final results of our annotation phase. This is what the data set looked like. I mean, it looks like in a graph, but in Unity, it looked like sort of a dictionary. Each of these are ranked from 0 to 1 for normalization concepts. And each of these behaviors are listed in a way where we now understand how a user, excuse me, how a user feels when this sort of behavior is exposed to them in a virtual scenario. So now we move over to our optimization phase. Taking into account, we have this sort of data available to us. We use the Monte Carlo, Markov chain Monte Carlo technique. It's called simulated annealing. And for our optimization, we had to develop cost terms. So we developed 3 cost terms, which we thought would allow us to accomplish our basic idea of how we can get the optimized values out. So we had the affect cost, which basically takes into account the total affect of the scene, the affect variance cost, how much from the central affect, how much variance we want in the crowd, how much difference we want in the crowd with the values itself, and then the duplicate behavior cost. We did not want behaviors to repeat for this study, because we thought that let's try out with unique stuff, because bringing in a duplication might cause some other things that we need to take care of. So every scene that we constructed, low, medium, and high, had a total cost value that we associated with it, and it was the sum of these 3 affect, variance, and duplication costs. Here is how the affect cost look like. The idea behind it is simple. If we want to break it down from equation form, it's every scene has its own average negative affect, and then the sigma A is what we provide to the algorithm. So the target of it is the optimization takes into account all the average, looks at the target, and then it tries to match up the average with the target until we get a value that's close to 0 or ideally 0. Similar is with the variance cost. Again, concept remains same. We give the sigma B, which is our variance, targeted variance, and then we calculate the existing variance of the scene, and then we calculate the difference between them. I'll explain how the final term is obtained in one of the future slides. And finally, the duplication costs. Here, the gamma function is the most important one, where we can see that if the gamma function, if the algorithm detects that there's 2 similar behaviors or the same behaviors, it gives us a penalty of the value of 1, which increases the total cost. So if the behaviors are same, we get a higher cost. And then if it's not the same, we get 0, which is again ideal. All of this drives the total cost towards being 0 or as close to 0 as possible, which was how we calculated which behavior to take. So this is how the optimization, after the optimization started, this is how it looked like. So we have 10 different scenes. We calculate the average effect, and then the algorithm knows the target effect that it has been provided. Then it removes one of the character from the scene, puts in another one, and then it calculates the average using that new character. So a new set of 10 characters are there, and it calculates the average. It correlates all these values from the dictionary that we had from our first phase. And then it does that until we reach either there's a less than 2% change in over the past 100 iterations, or there's almost a 0 total cost that's been achieved. And we repeat this for each of the scenes, and then we expose the final list of characters to the players. This would make it a bit more clearer. So I'll suggest people to think of it as like a traffic light system: red, yellow, green. Red is when the program is not running. Basically, we input our values. So we want 10 characters, and we provide a target affix. So we provided 0.7 for our high value, and then we give our target variance. Then we run the optimization algorithm. It tries to calculate all the proposed costs and stuff, and it brings things as close to 0 as possible. And at the end, we get the green part where it spits out a list of 10 different values. Now, these values are correlated with the existing database that we have, and that's how we decide which behaviors to choose. For the current time being, the only limitation is that this is manual. I have to manually look up some of the stuff and manually create the scenes. But there, if more time and effort was put into it, it could definitely become a automated process. And then the graph looks like that on the right, where we introduce the concept of simulated annealing is to introduce some errors in the middle so that we get so that we get a better score towards the end. That's why you see a jagged graph, but towards the end, over 200 iterations, the value remains the same. And that's when we stop the algorithm and we're accepting these last 10 different behaviors that the algorithm proposed. So overall, after the whole thing has been done, this is how the behavior table looked like. The green check marks basically indicate which behavior we took. So for example, walk across, look at intimate is one of the behaviors that can be applied. Yelling, look at personal is another behavior, and so on. We chose the three values. For the low value, we chose the target affect to be 0.3. This is for the medium condition. We chose the target affect to be 0.5. And then this is for the high condition. We chose the target affect to be 0.7. Another interesting thing that we observed is that in some of our literature study, it was said that gaze played the most important role in crowded scenarios where people felt more uncomfortable when the characters were looking at them directly. And here you can see that there's a gradual shift between look at and no look at. In high condition, look at characteristics are more in the crowd, and in the low condition, no look at characteristics are more for the characters. So it helped us get assured that, okay, we are moving in some sort of a right direction. So then everything has been done. We have our 10 characters, we have our low, medium, high scenes. Now comes the user study phase. This was a within group study. All of the participants experienced all three scenarios and gave their feedback using the scale that we developed essentially. For statistical analysis, we used a one-way repeated measures ANOVA. We wanted to compare the means between the different scenes. And for the final study phase, we had the character set to only 10 characters, just to eliminate all the visual inconsistencies and stuff that might occur and make it run as smooth as possible. Again, Latin square design was used to determine the order. So here I have a demo video of how the high negative affect condition looked like through the eyes of the player. Let's play it. That's a look at condition. And all of these characters have different behaviors attached to them. So some walk across your field of view, some walk towards you, some just turn around and yell, some point at you. That is it. That's a nice ending to it. We want the players to look at the environment as well. Right. Let us. Okay, so here's the final results of our user study phase. Our questionnaire also had some demographic questions in the beginning, where we asked them their prior experience to virtual reality and how much gaming they did per week, so that they understood, we could understand how much they understood virtual characters and virtual scenarios. A majority of them did have VR experience, did have experienced VR before, and a majority of them did have gaming experience that they had from before. So that was good to know. And here are the final results that we had. A total number of participants that we had were 57. And after eliminating the 3 outliers, we found out that the means and standard deviations of the low condition was 31.71, medium 36.73, and then high condition was 40.68, which basically showed a gradual increase. Here's the box plots of each of the scenes essentially, and we can see that there's a gradual increase in the trend. And to conclude, we found out that low negative affect scene was rated lower than the medium, and the medium was rated lower than the high negative affect scene, which is something that we wanted, which is something we were pursuing towards. The comments also indicated towards that the participants identified some of these negative scenes better because of the inclusion of the negative nature of the crowd. And also some of their comments were like, they felt threatened when they invaded the personal space, and they also felt threatened when someone was pointing at them, which pointed towards the direction that including proxemics was a good thing. It enhanced the the realism of the proof of concept that we tried to do. And yeah, proxemics was a step in the right direction. Thus, we addressed our research question. It can be confirmed that it is indeed possible to automatically synthesize multi-character experiences that induce a certain amount of negative affect in the participants based on a provided level of negative effect. Future extensions. Here, we discuss some of the branches that we want to go from this point onwards. We included these as a counter to some of our limitations that we had. For example, we want to increase the current behavior data set. We just took some of the basic ones that we thought of, and then we tried to build up a data set on us. Maybe in the future, someone will provide us, or someone will create a more detailed data set with numbers and values associated with those behaviors. So that would be something that we are interested in looking at. Even we are trying to develop some of the stuff. We want to enhance the current scenario with sounds. Right now, we wanted to eliminate sounds because then we had to increase the number of tests we had to do with and without sounds. We wanted to examine the psychological and behavioral responses. We have to take into account anxiety and emotional reactivity of the participants as well. And we wanted to develop this same idea, but with now we take into account the EEG and GSR techniques, which measure your physiological changes, and then we compare it what the annotated changes, annotated values compared with the physiological values were, just to see if there's a difference between the true values and the reported values. We also are looking towards developing more complex scenes, VR games, VR interactions, more design decisions. Of course, cost terms there are plenty number of cost terms that we could have included, but for the sake of simplicity, we just limited ourselves to 3. And then inclusion of behavior trees and event-centric scenes. We are looking at dynamically changing the crowd behavior and seeing if they actually notice the difference. Let's say some crowd scenarios become from more negative to less negative based on them doing a good deed. So those are some of the event-centric scenarios that we are trying to work towards. These are some of the references that we had in our slides. And yeah, that is it. Thank you very much. That's Professor Mousas, me, and Purdue University. Thank you.
Thank you. So, any question? I have a comment.
Yes.
Yes, because I think that the behavior, there is interest, found interesting the behavior, but there is something I have difficulty to accept, is that you use always the term of crowd. I have worked many years on crowd, and I cannot see just a few characters, maximum 10, and speak about crowd, because there is no problem of crowd in this paper. So I think the term of crowd should not be used.
Okay.
What do you think about this?
Well, we were discussing this when we discussed the exact same point when we figured out the thing, because I was like, Professor, do you think 10 people are enough for a crowd? Was that? So we, just to reduce a lot of the complexity of the scenario itself, plus the background that goes into it, the way of coding that I used and the way of simulations that we developed, we had to limit ourselves with our characters, because at some point there were repeating models in our final phase, which was one of the things that we said we don't want that to happen, because there were some studies that said that there came a bias when people saw the same person, let's say, but with different behaviors consecutively. So we knew which direction we wanted to go, and the 10-person limit was just like something that had to be done to achieve that direction. And that's one of our, exactly what we talked about in our limitations is we want this to be a more complex scenario. It definitely does not stay true to the word crowd, but we were using crowd as in the sense of a multiple collective of people. That's what we intended to do it.
Because the interest in behaviors is that we know very, very well that when you have crowd and when you have many people, the behavior of the people change a lot. So we have really a different attitude from the people when you have many people. And that's a problem you don't have here. is that
Yeah.
you have too less people to have this crowd behavior.
Right. I understand that. We definitely knew that there would be a limitation going in. But then again, we were like, this is a starters thing. Let's see where this goes, and we branch off of it. Our next event-centric stuff we are trying to do with clumps of crowded places. Some events take place where there's a lot of people crowded bunched together. We also take into account density and all that stuff. So it's a build-up. It's a build-up. That's what our plan
Okay.
was.
Okay, thank you. And